they gave us these amazing cups.
Oh, it's Taiwan, that.
Oh, Taiwan, right, yeah. And so the thing about these cups is that they've got a sticker on the bottom, so if you hit it like this, yeah, they don't fall over, which is great, right? And what the cup does do is if you just lift it straight up, it just comes right up. Except that's what my cup used to do. Now,
oh, they changed.
I cannot lift this thing.
Oh, no.
I have a new straw. Oh, there it goes. Yeah, just a little.
It's like, yeah, you mentioned like it's good for earthquakes. Yeah. The song is great.
That's right.
Might have to get an emergency straw, though. You can't get it off the table with a straw in it.
Perfect. So Dom is going to show us some of the work that he's been doing on mappings, and so there's 2 maps he's implemented. A lot of it's motivated by a project with Jeff, right?
Jeff, yeah.
Yeah, so he'll show us that, and then there's a couple pull request updates. I think there's 2 that are really close to ready to go in. So the discretized tree mesh cell grad and the DC pull request. So just like a couple things to chat about, and we can probably clean those up today and get them out, which would be really exciting. So
both of them you'll be relying on right away.
Yeah.
Then I get to start a new puzzle.
Exactly. Perfect. Dom, do you want to start us off?
Yeah. Good. So yeah, you said it right. This comes from a request from our strongest supporter, currently, Jeff Witter, who's doing geothermal work in the US. And he's doing mostly grab and mag.
Oh.
And then his problem was that they have a very good understanding of what's happening in the basement with the seismic. So they have a very good understanding of the big structures, the big layers of the area. And so he would like to be able to obviously recover those in the inversion. But he doesn't know what the values should be, what the values of each unit should be in terms of density. So that's always the first problem. So how do you invert for big units at the same time? So unit 1, 2, and 3 are going to have density of X, Y, and Z, right? So that's what he asked for in the first pass. So can we invert for this? And this is the homogeneous map that I'll show you later. This is basically to lump in all the cells in the inversion model into pure units. The other issue is that this is a synthetic model, but it kind of like summarizes this problem, is that if you look at the data map, is that he knows about the big units, unit 1, 2, and 3, but there's other stuff in it. So if you try to do straight up homogeneous inversion, and there's like high frequency content in your data, it's going to skew, it's really going to give you trouble, right, to invert to the 3 units, because the inversion is going to try to fit also the smallest features. So then you get the idea of like, okay, what if we just layer our inversions? If we could have both homogeneous inversions and at the same time have like full heterogeneity, right? So we can invert for both the units and then whatever extra stuff that is in the data at the same time. And that's the idea of then adding a summation. So we're going to summing 2 components, we're going to sum the 3 units plus whatever extra additional material there is. Those are the two maps, and then like if we do that, then we can do a pretty good job at inverting for model 1, 2, and 3, plus the additional blocks.
So that kind of like it's the homo math. It's very interesting.
No, I changed it.
So that like all the structures are fixed, and then you're just basically inverted for three parameters.
3 values.
3 values.
That's right.
And then after that, then using some map, you're inverting all of them together.
Exactly.
3 plus also.
Right. So your forward is a sum of two model spaces, model 1 and model
have you tried like a kind of what Mike did? Because like it's kind of similar ideas, but like he kind of started with parametric inversion and use that as starting model. That you're putting all of them together, but you could kind of, so your choice is you could start from here and then just do second inversion. Like, is that kind of
Yeah, I mean, in my mind, this is better because you're doing both at the same time. So you're not gonna move back and forth between two possible solutions. And the difference between this and just doing a reference model and working with a reference model is that here we don't need to know the values of the in each unit. So we don't need the reference model to be true values. They're just indicators that there's a contrast, and then now it gives me the value out of the data. That's the advantage over just using a reference model.
Do you know where about things going in negative? Because you're.
I can bound it, right? No problem. You can bound it.
Yeah. Yes, but I'm wondering about like bounding the sum. Bounding the sum is much harder to do because there's sort of no guarantee.
okay.
Each step
That's true.
that like we haven't actually. I mean, because if you're adding perturbation on top of a physical model, there's sort of no guarantee that it doesn't actually do something that's not physical. It shouldn't, but.
No, that's you're
There's
right.
no
Yeah, we would need to have a smarter projection. Smarter projections to take into account that there's a sum map. Yeah. Because then we could do the projection on the summation, and then both model parameters would have to be forced. Or we could do the prediction on one of the two.
Yeah.
Choose. So right now this is density, so it's not a problem. You can go both positive and negative. But it's a good point. It's a good point. Yeah.
But in the end, you might have like a global boundary put on any cell as far as the sum of whatever properties you got, right? But bound on the property, but that property value taken as sum. I just be part of that.
Actually, yeah, that makes more sense what you said again, while you were talking here, because let's say we were doing strictly positive physical property. We only care that the sum of the two is non-zero, right? We could have an homogeneous value that is high, and then the heterogeneity makes it lower, so it's going to be a negative heterogeneity. The sum is not the sum.
The other thing you could do too is it's a question of order of operations. Like for conductivity, if we're inverting from log conductivity, you just make sure the log is on the outside of the sum.
Yeah.
And then we enforce positivity on the sum. So,
Okay.
yeah, doing that afterwards as opposed to before.
Yeah. Well, maybe let's look at some code that will be more obvious. Okay, let's look at. I put a notebook together, and this will just generate the figures that we looked at. Okay, so this is a Mac. Actually, this is a Mac problem. So what I'm doing in the first cell is creating a flat survey. It's going to be from -20 to 20 meters. All my receivers. And then I'm creating a model with just, it's a block and a half space with value of 0.05 SI. And then I'm just gonna split the domain into two parts. One has 0 and the other one is 0.01. So the model looks like this. This is a plan view. This is the cross-section view. So it's just a block. And we have a unit 1 and then unit 2. We can run the forward simulation. Data looks like this. So there's obviously a big trend coming from the east, right? And it's kind of harder to see, but technically the block is in the center here. But because there's such a big trend, it's kind of overprinting everything. Okay, so first we can run the traditional smooth inversion, and here we're just saying that it's going to be 0, as close to 0 as possible everywhere. So I have a really hard time getting the domains right. The block is sort of the right place, but yeah, the inversion has a really hard time just because the assumption is wrong. Yeah, we're assuming 0, whilst there's actually a big trend in the data.
doing your reference model, and then you're using a sparse?
No, that's delta. Okay. So let me just check what did I run. Okay. Oh yeah. So the first experiment. What if we just add twice the same model parameters? We're just going to split the model into two of the same. Right? So each cell's going to have twice the same. So hopefully, I just get a model that's half the half the size of the other one, right? Because if we just have, like, I'll shoot that film here.
Actually, maybe before you go in, you just rewind a little bit and just say what you're going to do for regularizations here, both for the background model and also for the model, just between use for
Sounds good.
regularization.
So the first one, we're not even going to do a homogeneous inversion right now. I just want to show this one here, where we have one vector model parameters that has a number of cells in the mesh. All I'm going to do is split it in two.
I don't know if I quite follow. Splitting what into two, sorry?
So I'm just going to grab this guy twice. And I'm going to add this vector model twice to my forward operator. So basically, I'm saying use it twice.
Okay.
So hopefully, the recovered model here is going to be half the values that I'm getting here because I'm adding it to itself twice, to the forward twice. And that's exactly what happened, right? If you look at the peak value, this one is 0.008, and this one is 0.016, right? So I recovered a model which is half of itself because I added it twice to the inversion. That's just a test, like a sanity check to make sure that everything runs. Right?
I was going to say the sanity check, isn't it?
Yeah, exactly. Now, what I will do is that was it. So all I did is the sum map, and I just put two identity mapping. So I'm stacking twice the same model parameter. Okay. So that one ran, and then I got rid of that one that I showed you. Now what I can do is create split my model space in my two domains, model A, model B. So I know what the split exists. So I'm going to create an homogeneous map. And what the homogeneous map does is simply to I didn't put a picture here to explain it, but basically it knows which model parameters of that vectors exist or belong to group 1 and which ones belong to group 2. It's going to assign a single value each of these groups. And then when I do my forward model, I simply sum up all those cells times that value, sum all those cells times that value, and then do the forward. That's what the homogeneous does. So it's kind of a projection. Now I can join the homogeneous like this. Don't need to worry too much about the mechanics, but I'm going to stack an heterogeneous. That means all the cells are active, all the same cell size. And on top of it, I'm going to have my combined values. And then just add this to the forward calculation, so it knows which model parameters are due to the full heterogeneity and which model parameters. Does that make sense so far?
Your model vector, is it twice the length of your number of cells, or is it 2 plus your number of cells?
Yeah, so it's this graph here. So my homogeneous are like 2, 3, whatever how many domains you have. And that's stacked on top of your full NC number of cells vector. And then the sum map knows, take the projection of the first two, expand it to full, and then add it to the full vector. And so it does the summation of the parametric projection, and just the usual identities for the null vector. Add them up, and then do that for the calculation. I always forget the inputs in the browser. Okay. So we also need wires, right? We need wires because that's what those lines are. Those are the wires. The wires knows which ones belong to which parts. So I'm going to do my.
Did that just remind us? Probably our lingo. So what we've done with wires is it lets you take like a model vector and basically say like these 4 parameters are actually associated with something specific. So in an EM inversion, for example, you could say your model could be both conductivity and permeability if you wanted. So you could invert for both. Oh. But then you need to tell the inversion like these 8 parameters actually, these are going to map to conductivity and these ones are going to map to permeability. And so wires is just a helpful way to maintain that organization.
So the name wires is just other than
Connects.
it connects everything.
Yeah.
It tells
Yeah.
you or gives maps. Yeah.
It's a map.
Yeah.
That's exactly what it is. Yeah. So yeah, really, when the wires is just it's just a flat matrix that has the number of parameters, a full vector, and then it collapses it to whichever it wants to grab from that matrix. That's all. That's what it is. Kind of a flat matrix. It is a flat matrix.
Yeah.
Okay, and so some map. I'm doing it on a bunch of. Here there was a little bit of a scaling for the distance weighting or sensitivity types weighting. Need to figure it out. That one works pretty well.
And that's in your regularization, sensitivity?
Yeah, so right now I'm just computing a vector here, right? I'm just collapsing the rows of the sensitivities. I'm doing the opposite scaling for the homogeneous map because I want to preserve the fact that bigger units have a higher sensitivities. I don't want to kill that part. So I'm just going to divide it for now. So when I multiply it, it just does this trick. And then for the heterogeneity, it's just the same as usual. It's just the sum rows of the sensitivities. Now the regularization now has two parts, right? We have a part that is going to regularize the homogeneous part, and a part that is going to regularize the heterogeneous part. So I'm going to create 2 regularizations, and I'm going to add them up together. Because you might want to do something different, and I'll show you 2 examples. For instance, on the heterogeneity, maybe want it smooth, or maybe we want it compact. So we want to be able to switch.
So you can assign
whatever you want.
Either.
Absolutely.
Oh, that's pretty cool.
Yeah, it's fully flexible that way, which is nice. Yeah. So this is one example of what the sum map is doing, but now it's opened up to everything that you want. Right? Parametric conversions, like more complicated parametric conversions than that.
Jeez, this is quick.
Okay, so first do the L2, and then we recover this model. So we got value uniformly on this left and uniform on the right. Now you see there's an issue right now that I still need to figure out, is that because we're only summing, one side is going to have higher susceptibility than the other one. So I need to think in terms of regularization of regularizing the sum of both, rather than one at a time. Or I'm not sure. It's like open for research.
Can you rephrase it?
Yeah, like I can show you if you want just the heterogeneous. Right, so just the heterogeneous part, that's the L2, the usual L2 model. Right? Now we're adding this to a model that has domain 8, which is higher than domain 2. So we're just kicking up one side, right? Because the summation is going to be higher on the left.
Oh, I see.
Which might not be, is not a good thing in our case here, because
right.
we're kind of like overemphasizing them.
Ah.
Okay, we can rerun with sparsity. Here, I'm just going to do an L0, L1. Rerun the inversion.
That's actually really subtle. Because if you try and regularize on the sum now, it's going to probably try and
Kill that jump. Now, I don't be sure how it's going on. It's converting.
If you just look over your heterogeneous model, look at areas where you have like structure, so like with our non-zero gradient, and with inside those areas, just kind of take heterogeneous values. And then areas outside of that, take background values.
Mm-hmm. That would require, yeah, that's good. That's a good point. And then this part, so we're doing a pretty good job. If we ask for flat anomalies, then it kind of helps us out. But it's still a little bit higher on this side than it is on. But it's,
Did your background change a fair bit? Looks different than the.
Well, the thing is that the smooth model extends everywhere, right? So,
yeah.
So it will sort of add to both domains. Just what is the so if I do a wireless promo and then I multiply my those are the two values. So 0.01 and then smaller on the left. So this one is actually really good, right? Our true model is 0.01 on that side. And there's a little bit extra on this side. We could do sparsity on the background values as well, right? Here, I haven't done them, but let's try to break the code.
Like that means that you're pushing the other value to 0.
Yeah, let's try to push them to 0. Or to large enough, and let's see if that works. Yes.
You have chosen like a tough model.
Let's see if that works. Put it down. So yeah, well that runs. So that's the sum map in the these maps. I kind of like resurfaced some issues like in the way the derivatives were implemented. So I need to fix a few things. Because dimensions were not working. Like, how come dimensions are working? And I realized I was missing a bunch of like derivatives.
Like underneath the sum map, or
in the direct. Both in the sum map and in the linear problem, we had forgot to put our derivatives in there.
Right. Yeah.
So now we have derivatives of the mapping inside the linear problem. Anyways.
One question I have just on the name. Do we want to call, so some map I think is like pretty descriptive. Homogeneous map, I'm wondering if we want to call it something like surject units or something like that.
Like it?
So we've used surject to indicate when we're going from one value to many cells. So like there's the surject fold if you just wanted to have like inverted reference with, I don't know, something like that. Makes sense. Yeah.
Hey, what's the difference between the surject and do you invert on the with the surject?
So all of it, like, so we've got like surject and inject, right? Those
Yeah.
are the two that we use. So inject is 1-to-1. So when you're doing air cells, for example, we're mapping like exactly the number of cells now just to the air. So there's no change in number of parameters between one and the other.
Mm-hmm.
Whereas when you do a surjection, you're changing the number of parameters. So we go from 2 parameters to now like number of cells. We've populated all of our cells.
Okay.
So that's all that we try to use.
Now I'm debating If I have a feeling homogeneous is doing the same thing.
Yeah, well, all we have is the surject full. We don't actually have any other style of surjection map, I guess. So we only have one that goes from like 1 to.
I think
Or
we
a
have
1D
1D map, vertical 1D map. So I think, or your 4 modeling 3D, your 1D version, or 2D version. So we do have some of them.
Okay.
Yeah, so they're also like the similar class of maps, but all doing something. So
Okay. All right.
one thing.
So I created a PR for it. So then, and then yeah, it's not ready for. It's not really ready for review. It needs to pass. Needs to write some tests for it. And then Rowan started commenting. You commented too, yeah.
Yeah, you should have a couple little things.
Yeah. So I'll work on the slide lines. Yep.
That's exciting, though. Thanks.
What's the first motivational example for this that's really driving the development?
It's the Forge data set about I was talking initially. So it's not exactly this data set, but sorry, what was I? It's a data set that looks very similar to this one.
Your target is actually on the boundary, like on the interface. You're kind of like isolated target is on the interface.
Like it could be anywhere. Yeah. It could be on top. It could be anywhere. It's just like a problem where you have short wavelengths anomalies in a broad background. So you want to be able to invert for the trend and the heterogeneity.
I see.
Just one at a time is not satisfactory. Like the inversion at our time, if you don't account for heterogeneity at the same time, yeah, the values of your big domains is going to be wrong for sure, because you're including this in it, and then it's going to have our time conversion because it's going to try to fit this high p value, which has nothing for it to be able to fit.
Isn't it like I can like not criticizing, but if you do iterative way, the kind of one nice thing about you don't really need to worry about that like with scrap it like this sharp boundary at the end of your final. Let's say this if you do iteratively, I think you're just always doing full. So
that's true. But, yeah. Okay, so you would use a reference model every time. You would cluster in between. How do you go from one to the other?
Well, I think
because if you have a parametric, when you're in your parametric conversion phase, you somehow need to dump everything in.
Okay, yeah, that's true. So, yeah. Yes,
I see your point though. Like if you were doing.
What I was curious because like how bad it is if you just dot full, then it's like doing every signals and then just do the first path inversion of homogeneous map. Then I think how bad your map model is. If that is really bad, I think okay.
I think we should always assume that it's going to be really bad because there's always signal you're not going to be able to fill. There's always going to be like near surface anomalies or strong conductors or the thing that you're actually interested in. You're not going to be able to fit it because your geological model doesn't have that level of details, right? So, and then you're going to say, okay, well my inversion stalled because I can't fit it. But how do you even know that you fit it what you wanted to fit? You know, it's going to be okay. I stalled. I stopped. This is the best I can do. Okay, well, what did you fit exactly? You know, then you need to look at the data. I don't know. Yeah. It sounds like this is such an easier, more streamlined way to.
Yeah, it's much easier. It's much easier. Okay, I'm just thinking about like conventional way. Let's say, we can think about it as a regional removal, right? Like you kind of carve out. Let's look at that map. I got two anomalies. I have an idea. right? You can just carve out some portion of that, and then do a homogeneous, like using that map, and do an inversion, cover background, and then I can add those anomalies now, and then just, yeah,
That's a lot of steps.
that's true, that's true.
That's a lot of steps, and the Earth is not that easy. Like if your anomalies, if your short wavelength is like some like bizarre shapes, like you don't even know what the footprint of that bizarre shape extends to. And then the whole thing with regional removal is that, like, let's say we try to just invert the back, remove the trend. Then we try that with Jeff, and like my instinct initially when I would look at a data set like this, I would say, well, there's like a left to right, there's an east-west trend. I'm just gonna detrend the data and invert it, right? Danger with that is that there's actually signal. There's interesting signal that geologists want to know. They want to know where the basement is, what those dipping features are. And if you just blanket remove with a polynomial trend, you lost all your signal. Yes, you're going to be able to recover like the small features, but this is half the story. The whole story is like, what are the layers, what they look like.
They would get their two targets, and then they'd be asking, "Oh, what about structure?"
Yeah.
It always just leads to more questions. You can answer.
And yeah, when you remove trends to the dangers that it's a dipping unit, you might be killing the signal of your dip as well. So everything's going to end up like being straight vertical anomaly, which could not be reality, right? Anyway, it's a first step. It's just a mechanics for it. You can experiment. Right? Jeff will experiment for us. So he'll let us know how that works for him.
That's exciting though.
Yeah, pretty fast actually, yeah. 2 weeks of work. And then now it's running. And then.
Yeah, so other things, do you guys want to like briefly chat through just the two major pull requests that are on right now? Sorry. We'll go over here. Hope that that's screen sharing. There is two big changes coming in probably this week. Dom, do you want to briefly just give an overview of what's going on with this PR and what you see as the status?
I think we're almost passing, right? It was just a bit of coverage that was missing.
Yeah, so what Dom has been working on here is...
Well, these guys work hard too, yeah.
Yes. Has been working on the cell gradients for the octave methods. Because if you sort of take a naive approach, what ends up happening is you get large tears in your model where cell sizes change. And so, yeah, where it courses. So, because if you use, like the naive approach is to use the transpose of the phase divisions, and that doesn't account for the fact that like all of these 4 cells, for example, should be the same as the one big cell.
Yeah, that's right. Yeah, that's exactly what it is. So you ended up with the longer gradients on the interface, so you're over smoothing every time you change the battery level. Yeah. So now it's pretty good, right? Like so the top was before, and now the bottom is so it looks a lot more like what a tensor inversion would give you. Obviously, you have like coarser cells, but you don't see as much the interfaces, right? You have the smooth gradient. Most if you look this, no, it's that way.
Yeah.
And Mike, you've been testing this quite a bit. Yeah.
Yeah, on that PR, there's now all the gradient operators tested for the DC problem, right? So that was pretty big too on this one. What did you end up doing? I kind of passed through it, but you took the cell phase div and then just added the dimension or something to it.
We did a couple different things now. I'm not sure which one ended up sticking. We played around with some. So I'd have to go back and look at the code and see which ones we're actually using now.
Are you using TikTok or is it?
No, for
For the testing stuff.
to be able to use the.
No, I think I was using, not a, what's it called, a uniform mesh. There's like so there's one for taking account of volume, and then there's one for the other, which doesn't take account of volume. I think, so you worked on without volume.
Yeah, that's right.
So I think Mike and I was working on with volume. So I wasn't following what Dom did. I was using a simple trick for a rig formulation, and basically using the given fixed div, and then just multiplying the product. You could actually get the equivalent cell gradient for normal formulation. I think that's what we did.
Okay. Just one question I had, so it's being tested on a uniform tree mesh, but not on a random tree?
I think if then we may not get a second order accuracy. I think, yeah, I'm not 100% sure which test I did. I think I was basically following the other test.
Yeah.
Done in tree mesh, so I wasn't really kind of sure what's really expected. So my guess is for the non-uniform cell from the tree mesh, you're expecting first order accuracy. That was my guess, but wasn't quite sure.
Right, that's one we can dive into a bit, because I think it should, doing it right, it should be second order accurate.
Right. There's a couple of things because even though like there's a uniform, it's not like it's not quite uniform. What the test does actually it generates a circle and then refine in the circle, and so it's not quite what we think a uniform mesh.
So it calls itself a uniform mesh.
Oh, but it's
There's definitely
actually-
refinement and there's definitely structure.
Okay, so it's using
Yeah, I think
uniform
this,
cells.
yeah, cell size is
Yeah,
kind of it's
size.
uniform, but not there's a it's offshoot.
Okay, fair enough.
That's a feature that we'll probably want at some point to be able to do the tree meshes squish, like not with identical dimensions.
Right. Currently, what we could do is basically just a sheet, right?
And it splits. Yeah.
Yeah.
Ideally, we'd like to be able to chop, just draw a rectangle and box.
Yeah. Yeah, on that PR, we were just talking about it. We need to finish the saving functions. There's a change in space, right? So.
That's true.
It's just that one that I've really noticed. It's so save the models, it's just when you're trying to follow your term misfit.
Is this in DC or is it actually
No,
associated
that's
with
in
DC?
directives.
Okay,
The saving models.
sorry, but it's on the DCIP dev
Yes,
request.
yes.
Yeah, so this has been.
Oh, sorry. Yeah, you're right. You said yeah, that was nice.
Yeah, Soggy, do you want to give a quick update on this? This?
Well, it was a long history. I guess. And, I don't know, 6 months or something. Is that November?
April.
I think the description is not including everything.
Yeah, I think there are, initially, that was by starting, I just implemented the 2.5D DC problem and mixed boundary condition. That was to handle the pole data. That was the initial initiative, but the other things happened, and we just lumped in all of the Mike's and Thibaut's updates to here. It's like a lump sum of. But I think all the features, important features, are actually having a 2.5D DC and IP, and a mixed boundary condition for a cell-centered problem, so you can handle pole data. And there are a whole bunch of utility codes that, like kind of practical tools that you can compute the geometry factors and parent resistivity for some IOs, at least like with the idea of location and read in. We have a UDC IO, so if you have a UDC format, you can read in and do formal conversion for using SimPEG codes.
So if we had like older projects that had UDC code, we wanted to put into SimPEG, we just use that file or?
Yes, yes. Yes, I think, yes, yeah, we tested. It works. I'm not 100% it'll work for every case.
Like most of them, like I tested it on for DCIP or like the DCIP 2D and DCIP 3D code, and with like surface or general format data. So that should work for most of them.
Yeah.
If not, create an issue with it.
Yeah, I know, something I jump into right away, but it's.
There's
Cool.
simple plotting functions. There's plotting supersections and stuff. It's not fancy, but just general basic function.
Yeah, so hopefully we can get that in today or tomorrow.
Yeah.
Exciting.
Okay.
Yeah, are there things you wanted to show or chat about? We can chat online, offline.
Maybe just start offline first, just because like,
Yeah, for sure.
I kind of need to know stuff, or how I can contribute to that offline.
Yeah, for sure, for sure. While we're still online, do you guys have anything else you wanna add? We started the blog again. So there's now a blog again. Perfect. That's all I have.